Thanks very much, David. And thanks for coming. It's nice to see so many friendly faces. And thank you to IABSE for the medal. It's a great honour, and I'm rather humbled by some of the previous recipients. I can see one of them in the audience there, so hopefully I'll do it justice. The medal is awarded to an individual, but I think that design is a deeply social process, and we rarely do this in isolation. And I owe a great debt to all the people that have taught me over the years, and particularly to my current team at Structure Workshop, many of whom are here, and many of whom were instrumental in the projects that I'm going to show you. So starting with a little bit of context, if you don't know my background, the first project I ever worked on after graduation was Crossrail, now known as the Elizabeth Line. And I was conducting settlement studies above the running tunnels down Oxford Street, and that opened 30 years later. So it gives you some sort of understanding of how amazing that project is, actually, the amount of combined effort, the amount of people that must have been involved, and how long a project of that sophistication takes, you know, the gestation period. It's an incredible project, and it won the Sterling Prize last year. And that was the start of my training in heavy civils. I was working as a tunnel designer for Mott MacDonald in Croydon. And that included lots of work in the UK and abroad, some of which was on site. And I spent 18 months on site in the Medway Tunnel, which is the tunnel that you can see there on the right. Big stuff and some formative experience in the fundamentals of engineering. However, whilst tunnel design was fascinating and I really enjoyed it, it's difficult to imagine a discipline perhaps with less potential for self-expression. So after qualifying, I took some time out to work in a small bronze foundry in West London. Still noisy and dirty, but much smaller scale and much less regulated. And I really enjoyed that too. The satisfaction and interaction of physical work, as well as the cultural side of casting art. Amongst other influences, it was this combined training that has informed my approach. So when I founded Structure Workshop in 2004, it was with the aim of creating a practice where design and making could be more connected. At the heart of this is a love of design and an ambition to contribute to culture. And whether the project is a piece of furniture or a public building, that object is always the same. A lot has changed in the years since Structure Workshop's inception, but we remain a small practice, currently 12. And our design office, which is in a cobbled yard in South London, has been a constant throughout. These buildings were constructed in 1886 out of high quality stock brick and timber, and they combine workshops and tenement flats in a compact plan. Their simplicity and ongoing utility is a constant reminder of the enduring role of well-crafted buildings with good bones, and I think is something to aim for in our work. Over the past couple of months, I've been working on a project with Jamie Faubert and his team, a proposal, during which they tabled this drawing by the French hydraulic engineer Joseph Abe. I asked someone how to pronounce that earlier. Describing his patent for a voûte plate, or a flat vault. This was drawn in 1699, and it's from an age where etching and reproduction were costly, so it's concise and considered. It's both technical and full of imagination, beguiling even. A great excuse to make a model. And a great excuse to spend Saturday with an old friend in his workshop in South London, talking about some fella from the 17th century and manifesting his idea into the physical. So together we milled up an old tabletop, made a jig, and cut a series of polyhedral modules. That stopped moving. Oh, sorry. And immediately our understanding improves. We gain a better appreciation of the parts, the way in which they tessellate, and their combined ability to connect without fasteners or glue. It also looked just like the drawing, which was encouraging. And it works, it spans. But what's interesting is that in making the model, it reveals characteristics that aren't immediately discernible from the drawing, The modules are really sensitive to rotating out of plane, and consequently the system is prone to collapse. Perhaps it would be improved with a shoulder that locks each piece in place, but that would make it harder to make. And how would you make a jig to do that? And would a mason be able to do that? And you're off, basically. The design process is enlivened by making the model. Reciprocity is something we'd already been looking at with Carmody Groark Architects. This is the recently completed Art Play Pavilion at Dulwich Picture Gallery. This reciprocal arrangement of beams is similar. Each beam supports two beams at mid-span and is supported by two others each end, and together the beams form a sort of two-way spanning mesh. But here the supports are simple. They actively allow rotation, unlike IABSE Voetplaat, which relies on horizontal restraint. Carmody Groark wanted to use a UK-grown solid timber, Douglas fir, and the advantage of the reciprocal frame is that it only requires short lengths, which we felt provided more opportunity to secure high-quality, defect-free timber. Despite this apparent simplicity, we were preoccupied by the connection details. So again, we looked to a model, this time to inform more specific questions. This is Dan Doak and Polly Natanchuk, who were responsible for delivering the project at Structure Workshop. Should assemblies start from the corner or from the centre? Turns out it doesn't really matter. How significant was cumulative slip in the connections? Pretty significant. And how might tolerances impact on the overall geometry around the perimeter? It's hard to say, actually. And in case you're wondering, we don't normally drink red wine when we're working, but it got late. But of course, engineering is more about materials than mathematics, particularly when designing in a natural material like timber. We wanted to check that our expectations of the timber could be met. So we turned to the expertise of a timber yard in Wiltshire called East Brothers. The subsequent discussions ensured that the pragmatic sourcing, cutting, drying, milling, and grading of the timber was rolled into the design, ultimately resulting in a high-quality supply that met expectations. And that process continued subsequently with the framer Timber Workshop, who added their practical knowledge to the mix, feeding into the design process, how to control moisture content during fabrication and installation, the practicality of our connection detail and how this might be improved, and allowed us to communicate our thoughts on sequence and tolerance. And the result is an exceptionally crafted building built from high-quality local material. Whilst we have complete control over our drawings, our influence over materials and workmanship is more limited, and that's why proximity to making matters. So I'm going to show a series of projects that I've worked on, all where craft and material exploration have informed the process, and hopefully demonstrate how this approach leads to solutions that are both technically resolved and rich in character. The first is the Fenland Black Oak table, the closest we're going to get to a bridge this evening. The table is made from bog oak, the nation's rarest and most precious native hardwood. It's the magnus opus of master craftsman Hamish Lowe. For the past 30 years, Hamish has befriended the Fenland farmers, and now and then, when a farmer hits a piece of bog oak with the plough, rather than drag it to the side and burn it, they call Hamish. So this story begins 5,000 years ago, when an ancient forest of massive oak trees once stood deep within the Fenland Basin of East Anglia, much, much taller than the oaks we have today. Over time, and due to a rise in sea levels following the last ice age, these spectacular trees fell into the silt of the flooded forest floor, and there they have laid, preserved in the peat in anaerobic conditions for 5 millennia. In 2012, on a farm in the Whittington Fens of southwest Norfolk, a 13.5-metre section of one of the greatest of these buried giants was unearthed, from a tree so tall that the taper was indiscernible. Thankfully, the unique nature of the timber was recognised and the tree was retained whole. Planked in situ, the quality of the timber was revealed for the first time, and it's completely mind-blowing. Perfect timber from the Bronze Age, carbon dated to 3300 BC. That's 1,000 years before the bluestones of Stonehenge. 10 magnificent, breathtakingly beautiful consecutive planks, unlike anything seen before. Black oak needs to be dried artificially and very slowly. So over a period of 9 months, 1,800 litres of water were extracted from the planks in a purpose-built dehumidifying kiln. The planks shrank to almost half their thickness and a quarter of their width, and even 150 millimetres in length. And I like this picture. It says something about the shared endeavour. And our protagonist, Hamish, is in the orange. The planks were retained full length, and many new techniques were developed at the Building Crafts College to work on their unprecedented size. And here, the unique river joint being set out, carefully cutting and matching the full length planks to one another to ensure that it maximised the use of the existing timber. The craftsmanship was exceptional. It was a simple decision to select bronze as the material for the base, and we developed a series of concept designs for analysis. The table obviously needs to be strong and stable, but if it was too stiff, it wouldn't conform to the uneven floors that we predicted for it. Not stiff enough, and the cantilevering ends would bounce or rotate, making it unsuitable for a drink or a plate of food. It had to be just right, because there's no putting a beer mat under this table, I can tell you. It also had to allow the timber to expand and contract according to its moisture content, and the table is huge and weighs more than a ton, but it needed to be moved by hand, and it needed to be split in two to allow for transportation. Plus, it had to avoid damaging a cathedral floor. Ely Cathedral had agreed to display the table for 18 months, but we had strict limits on the point loads. And finally, it needed drop leaves. We'd been asked to design a mechanism that allowed 3 people to collapse the sides. So cue prototypes and exercise, rolling bits up ramps and developing leaf mechanisms. Ultimately, we selected a vertebrae type design, foldable ribs cantilevering from a torsionally stiff spine. And this photo is at Benson Sedgwick's in Dagenham. We could predict the behaviour of the bronze very accurately, but there's no substitute for having a bounce. And you can see Joe testing the cantilever on the left from Structural Workshop. And this provides a sense of the scale of the table and how easy it is to move. And of course, those long drop leaves. The table is currently at Lichfield on a slow tour around the cathedrals of England, and it's the most astonishing piece of timber that you can imagine, something I think is of international significance. But it also carries a stark reminder, not only of the depleted scale of our native trees, but of the real threat that climate change presents. The flooding of the low-lying forests led to the total loss of something that was probably thought to be indestructible by the people of the time. So from cabinet making to carpentry, sticking with timber though. This is Homerton College Dining Hall in Cambridge, designed with Field and Fowles, who were appointed as architects following an international design competition. Alongside kitchen, servery and buttery, the project called for an emblematic centrepiece, an architectural composition to reflect the ambitions of the college and to relate to the rich and diverse mix of buildings around it. The unlikely roots of the design, however, lie in a series of modest temporary structures on a brownfield site in Waterloo, the first of which was Field and Fowles' own studio. It's probably as straightforward a structure as you can imagine, a post and beam frame that a first-year university student could design. But despite that simplicity, it demonstrates many of the characteristics of structural design that I'm interested in. A legible structure, very lean and simple here, express material used with skill, and a set of carefully considered details or connections. And then ideally, these aspects combine to articulate something about the ideas behind the building. And for me here, it's simply the size of a piece of plywood. The lateral stability of the structure relies on a roof diaphragm to transmit wind loads to shear walls at each end. And as such, the continuity of the plywood sheathing is necessary. The door sets that you can see on the left are 1.8 metres wide, which provides the grid for glazing and primary beams. But anyone that has made something from plywood will know that it comes in sheets that are 2.4 metres long. So cutting these down to suit the beam spacing would waste 30% of the plywood. So by ripping the sheets in half to suit the purlin spacing and by staggering the sheets, an effective diaphragm is formed that results in no waste. The only thing you need are a set of noggins where the sheets are butt and where they must miss a beam. The depth of the beams, purlins and noggins half sequentially, and the noggins march across the roof in thirds. And it's an asymmetric arrangement based on an efficiency of material It's evident, but only if you care to observe it. But even if you don't, I think it subtly contributes to the liveliness of the building. The next building is a barn that bookends the same site. And this is one of my favourite projects of all the structure workshop projects, despite its simplicity. Again, the structure is expressed and legible. Here, it's a little bit more playful. Distorting the central tied truss into a diamond has provided the building with some identity. And again, the articulation of the connections contribute to the quality of the building. The design is intended to make the structure as simple to build as possible, and the connections use plywood gusset plates, carefully set out, enabling them to be CNC cut on a router. The framing members then have single straight cuts each end and are simply zipped together with screws. And with no steel flitch plates, the frame is extremely low in embodied carbon. The carpenters said they loved it. Well, that's what they told me anyway. And this is a bit of an aside, but at the time I thought we'd been mildly inventive to use plywood in this way until I encountered this rather handsome aisled barn in Devon, also using plywood gussets, but a good 40 years older. And so when it comes to making stuff, it's useful to remember it's usually done before and often much, much better. So when we came to design the dining hall project, it was the continuation of that existing relationship with the architect, discussing, deliberating, sketching and calculating together, creating designs for many built and unbuilt works, alongside a shared language of designing in timber and a mutual interest in low-tech, highly crafted forms of construction. The brief for the building called for a sustainable and robust structure with a design life of 200 plus years. And it was the timber frame that captured our imagination as we began to develop the design. That and the adjacent listed IABSE building that can be seen here on the right-hand side. Steeped in the arts and crafts, the rich detail and material quality of the building acted as a signpost for the project, a reminder of the potential the materials and workmanship have to provide that legacy. Though unconventional, the butterfly truss is stable as a 3-pinned arch, but we found that it was difficult to develop enough stiffness in the long, slender columns to resist spread or sway. Our solution lay in harnessing the buttressing effect of the walls. By providing restraint at the bottom of the lower rafters, they act in compression only, creating a stiff point right at the centre onto which the roof can span. This principle is similar to traditional Cambridge halls and chapels that use buttresses to counter the thrust of their vaulted ceilings. This time, coppiced sweet chestnut was selected as the timber. Coppicing retains the root after harvesting, making it unusually sustainable, even for timber. And by cutting out the knots and defects and laminating the laths into deep sections, long and highly engineered members are possible. Unfortunately, though, for us, not quite long enough, and the timber was not available in the lengths that we wanted that could span the 15-metre wide hall. A stable 4-way connection was required right at the centre. It was this connection which was informed by how things are made and which we explored in the office with a series of mock-ups that ultimately resolved the truss, a bridle joint with interlocking tenons. The final 1:5 model was later exhibited at the summer exhibition at the RA, which I think illustrates the appeal of combining engineering with craft. In fact, each of the connections in the frame tighten up under load, and this meant that they could be designed without any steel plates or bolts, instead being fastened with oak pegs, here being fabricated at Constructional Timber in Barnsley. And the orange ratchet straps are used to hold them together whilst they're test assembled. Our approach to celebrate materials and craftsmanship extends through the project. Seen from the south, the ceramic facade rests on a pigmented concrete plinth. This is faience, a tinned glazed ceramic familiar to pubs, tube stations and Victorian museums, and it was made by Darwin Terracotta in Blackburn. The load-bearing pots are made in traditional plaster piece moulds out of refined European ball clay, and together with the architects, we explored the geometry and the bond to accommodate shrinkage in production and movement in use. When combined with the diversity found in the glaze, the result is a facade that is rich in detail and variation, despite its bulk, and full-scale mock-ups were produced to ratify the approach. A similar attitude, marrying process with design, was taken to the boardmark concrete. Again, the colour and the diversity and the impression of the timber grain serve to temper the concrete, a material that can easily be harsh or blank by comparison. And here was Sophie Frith from Structural Workshop, who played an instrumental role in the project right from the start and right to the finish. It's a testament to the creative process that Freudenfels curate, that a building of this scale can express craft and making so completely. And I think it stands as an example of what can be achieved when the character of materials are expressed and leveraged through design. An arts and crafts building for the 21st century. My talk's not focused on embodied carbon, but in the midst of a climate crisis, carbon has to be seen as an arbiter of what is and what is not good design. Considering the inefficiencies of the hall, it's got 3 stories and 1 floor. The quality of the materials used and the ambitions for the design life, it performs pretty well, achieving an iStruct-E scores rating of B without the faience. But this drops to E with the faience. So how should design quality and design life impact our thinking in terms of carbon? And should we be talking about value for carbon instead of simply kilograms of CO2 per metre squared? The clear imperative is that we should be taking a retrofit first approach to construction, building only when necessary. Often this is deemed to be unpractical, and I think we're predisposed to see buildings as finished articles rather than buildings that can change and learn as the world changes around them. And the most compelling case I think I have for this is a set of dilapidated buildings in Hackney, which were bought by the product design company Pearson Lloyd to act as their new headquarters. Frustrated by the cost and the waste associated with the design of a new building, the clients, Tom Lloyd and Luke Pearson, asked to meet me on site to have a look. And it was this meeting and the conversations that followed that led to the buildings being retained. Their potential was not immediately evident, but after years of altering old and existing buildings in London, it was clear to me that they could be saved. To adapt existing buildings, they need to be understood. And it was their simple construction, our ability to identify and address defects in the existing fabric, alongside a collaborative contractor that unlocked the potential of the site. The workshops included 2 bays of traditional 19th century construction, the left-hand side, brick and timber, and 2 bays of late 1980s construction, the right-hand side, steel frames, with a very poor quality infill in between. Critically, foundations were retained, and second-hand stocks and timber were used to restore the Victorian parts. The steel frame was raised and back analysed to ensure high levels of utilisation and reclad. And the completed building is recognisable but transformational. The secret ingredient here was the lead designer, Cassian Castle, who acted as both architect and builder. This, in combination with an engaged client, allowed opportunities the building presented during construction to inform the design as the project progressed. The result is a building that's rich in character and rich in history, that celebrates retention over replacement, and which has 1/3 of the embodied carbon of an equivalent new build. It's better than a new build, and it was facilitated by early open conversations about expectations and a willingness to be led by construction rather than to dictate design. This adaptation of buildings has happened since time immemorial and has only become less common as construction has become easier with the advent of corporatized materials and machines that run on diesel. In 2017, we added a pavilion and link building to the Freightree building at Carlisle Cathedral. Despite being Grade 1 listed, the building has been constantly altered and chopped around. The east wall of the Freightree is 13th century and the crypt is thought to be 14th century. Much of the building was rebuilt in the 15th century and again restored in the 17th century. It's been used as a monk's refectory, a brew house and a barn, a school and a library. In the early 19th century, it was converted into a chapter house by Smirk and a new door was added to the north wall. And then in the late 19th century, it was changed back into a hall by Street and the door was reversed and tucked under a new porch. And this photograph shows the Smirk door with its inside outside and the porch removed. It was taken just after an archaeological excavation for the new link designed to connect the crypt to ground level and the ground level to the Freightree level. The proposal was to re-reverse the Smirk door and create a new door into the crypt. But excavation revealed a series of horrors, including a Roman drain under the door still running with water, and evidence of stone underpinning on the right-hand side, the corner of which had visibly dropped. It was this arrangement that we had to contend with. That's the background anyway. The process of reversing the door was a slow and careful exercise in stabilisation, the design of temporary works to support the medieval wall, followed by the sequential dismantling of the smirk door, all the while labelling the stones to enable reassembly. These works to the door were very much led by the stonemasons, Askins and Little, and as the door was dropped, it revealed the graphic cross-sections of the mouldings alongside original masons' marks. And if there was ever a photo that said design is in the making, this might be it. This is the restored phratery with the smirk door reinstated level with the floor at the back on the right, making the hall fully accessible for the first time in 600 years. And the door itself, with the outside inside and the inside back outside in its rightful position. The evidence of successive alterations is clear to see around the original door, in the new stone under the relieving arch, which is where we propped, and in the making good of the reveals on each side. And whilst the ornament on the outside is beautiful, the evidence of repair on the inside, I think, is also equally beautiful. Working alongside such skilled craftspeople was inspiring, and it was interesting to see how the relationship between the design team and the masons permitted their deep practical knowledge to inform details of the new stone arches of the pavilion. This was originally conceived as a machine-cut profile, but ultimately cut by hand. And that relationship between old and new and the sharing of lessons between dissimilar objects is one that is rich in potential and again rooted in making. On the left-hand side is Paradigm, a large-scale sculpture that we had designed previously for the artist Conrad Shawcross outside the Francis Crick Institute at St Pancras. And on the right-hand side is a photograph looking out through the smirk door showing the bronze die-grid roof over the Link building. The structural approach to 3D modelling, profile cutting and fabrication are essentially the same, one project informing the other. Similarly, our work in building structures has the potential to inform our work in the arts. We're currently nearing completion on the newly restored Gilbert Galleries in the V&A at Kensington. And as part of the project, we've reinstated the enfilade within the Falk Residences building, which is again Grade 1 listed. The original brick arches had been brutalised by a 90s office conversion, and it's a unique feature of brick as a material alongside the skill of the bricklayer that the reinstatement of the fabric is possible in this way. Of course, handmade bricks are brittle and variable, and individually they are unreliable, yet together in lime mortar they combine to have this enormous plastic structural potential. Our codes allow for this variation via the concepts of characteristic strength and material factors, ensuring that our masonry remains in a redundant state. But what about other materials where the hand of the maker and variation looms large? The simple solution is to load test, which is how we justified 800 plaster face casts on the current 4th plinth in Trafalgar Square. And similarly and more significantly with Ellen Atswee's turbine hall installation. These large-scale fabrics are made entirely from flattened bottle tops, wired together by hand with copper. The scale and detail is hard to believe, even when you're standing in front of them. The black curtain was 30 metres high and weighed 1.5 tons. This is not really a scenario where the engineer draws a drawing, develops a design and specifies something for construction. Rather, the entire design process is conducted in parallel with fabrication tests and often alongside the final fabrication itself. This photo shows Alistair Barnard from Structural Workshop talking about the support system with Edward Oliver from the Whitewall, fabrication company that we've worked with for 2 decades. The relationship is critical as it facilitates the process, design again informed by making. Another long-term collaborator is the London artist Conrad Shawcross. Conrad and I first started working together in 2006 on Space Trumpet, and we've not finished working together since. Conrad at that time had been commissioned by Unilever to deliver a kinetic work for the atrium of their building on Blackfriars Bridge in London. It was a significant project for me, being the first permanent artwork I'd worked on that was overtly structural. Conrad's work, I have to be careful here because Conrad's in the audience. Conrad's work sits at the intersection of art and science. Can I say that? And he'd been inspired by early warning systems, listening devices like the one shown on the left, and his early sketch for the work is shown on the right. His work at the time was predominantly in timber, and I look for structural inspiration in precedents. For example, the structure of the arms, which were to support large trumpets, were inspired by the structure of biplane wings. These are essentially a torsion box designed to stop the wings rolling off the back of the fuselage. Conrad builds all of his works himself, and the problem at that time was that his workshop was fairly rudimentary with little quality control. Can I say that? How then to reconcile the need to assure robustness in the structure hanging overhead with the artist's approach to fabrication? I often think that at the heart of structural engineering is the need to gain sufficient confidence to take responsibility. It doesn't really matter how that confidence is gained, but it must be there. Intuition, precedent, calculation, load testing, all are valid approaches. Typically, the design intent is then enforced through a specification, but that approach was not going to work here. My solution was to duplicate all the primary load paths, each part carefully designed, but if one part of the built structure were to fail for any reason, a second load path was there to carry the load. The structural design was defined in a set of 2D drawings, including the patterns for the trumpets, all connection details and the bearing design. It hangs from the flying carpets designed by KPF and Arup, and amazingly, when we switched it on, it worked, turning on 2 axes. And it still repositions at midday every day, almost 20 years later. Looking back at those drawings is interesting, and as I said, they included all the connection details, even the bearing design. Drawing, I think, is the bridge between design and making, and to me has a firm foot in both camps. By sketching, a design is brought into being, and in drawing, the system of construction is resolved. As designers, we'd ideally do both, but whilst I still sketch all the time, I rarely do a drawing these days, and that distances one from the real detail. Since we completed Space Trumpet, our combined experience has grown, but at the same time, design tools and fabrication methods have also radically advanced. This is another kinetic work from a few years later called Nervous System Inverted. Also designed in 2D, but by this stage, Conrad's workshop was better able to meet demands of the structural specification. And where uncertainty remained, in the worlds, for example, targeted testing could be carried out. The sculpture is a working rope machine concerned with planetary motion. You can see the machine supported at the top of this tower and the rope piled up next to it on a winch in the floor. We designed the tower specifically for the installation in the Mudum Gallery in Luxembourg. Again, looking for precedents, the structure was inspired by the structure of a gasometer. Conrad's most recent kinetic work is another rope machine called Umbilical, commissioned by David Walsh of the Museum of Old and New Art in Tasmania. Temporarily tested and exhibited recently at Here East, it's currently been dismantled before being shipped south to form part of the museum's permanent collection. And it's a project that has been more than 10 years in the making. Coincidentally, its kinematic envelope is exactly the same as Space Trumpet, but the approach to design and fabrication is a complete world away. Certainly its ambition and complexity is not something we could have resolved then, and even now, it presented us all with significant challenges to overcome. The machine comprises 135 spools of cord on quaternary arms that circle tertiary arms, which circle secondary and primary arms, all powered by a single motor. And over the course of a year, it produces 300 meters of rope, equal to the length of the cord on each spool. Each arm is asymmetric, and the diameters of the individual cords vary. The gear ratios between arms are such that the motion is aperiodic, and the machine will never repeat. As such, it produces an asymmetric rope that represents the state of the machine at the exact time that it was made. And it's akin to the motion of the solar system. Far from the moon and orbiting the Earth and the Earth orbiting the sun in neat elliptical orbits, the solar system as a whole is hurtling through space in a wildly complex and aperiodic trajectory. As engineers, we define the root geometry, which, despite the asymmetry, is rule-based. It's set out around 3 sides of a pentagon with asymmetric arms relating to one another through a spherical fractal arrangement, with each arm within an envelope that means that individual spools can't collide. That's the left-hand image. In turn, each generation of structure and mechanics occupy an onion ring, which again prevents clashes during the movement, the middle image. And it's a mix of imagination and careful definition, trying to find a pattern in the chaos. We ultimately developed and maintained a 3D parametric model that enabled us to coordinate with the artist and the mechanical engineers, ending up in what is essentially an artwork information model. While Space Trumpet has 9 2D drawings, Umbilical has a single coordinated 3D parametric model that all fabrication can be based on. And this is an image of the grasshopper definition of that parametric model. With so many components and mechanical forces and a machine that never repeats, it was a challenge to define the loads and the load paths and to establish a comprehensive set of possible load combinations and permutations. Add to that the complication of cyclical loads and fatigue and the changing balance of the machine as the spool's empty, and you start to see the scale of the design task we were confronted with. The fabrication and assembly was equally challenging, and it's a huge testament to Conrad's dedication to maintaining production in-house, that it was made in the same workshop as Space Trumpet, albeit transformed in terms of capability. Again, contrary to my inner fears, the machine worked perfectly, and it's worth pausing to enjoy that motion, which is asymmetric and aperiodic. The last project I'm going to show is a dinosaur called Fern. The artist was Evolution, and the fabricator was a company called Factor Mate. Factor Mate were founded by Adam Lowe, and they have an innovative approach to fabrication, merging digital technology with traditional craft skills. Their workshops are based in Madrid, and it's an Aladdin's cave of artifact. The work in the middle that you can see is a recreation of a Roman sculpture, the Colossus of Constantine, which we provided the engineering for. But it's also worth noting some of the other works covered in dust. The Lamassu, or winged lion, whose head you can see poking out from the left from the British Museum. And Leonardo da Vinci's Last Supper, just casually hung on the wall above. All facsimiles, of course. It was during lockdown that Adam called me to say that there was a competition to design and make a new dinosaur for the Natural History Museum, and that we absolutely must do it. It became a project where the traditional boundaries of the designer and the maker were blurred as our different areas of expertise collided, learning from each other and solving problems together. This time the story begins in the late Jurassic period. And 150 million years later, in 1898, railway engineers in Wyoming uncover a gigantic thigh bone. Dinosaur mania ripped through America, and an industrialist funded the dig. When it was formally described, it was named in his honour, Diplodocus carnegie. In an example of Anglo-American diplomacy, Carnegie gifted a plaster cast of the fossilised bones to King Edward VII, and it was this plaster facsimile that was displayed in the Natural History Museum for 120 years and became affectionately known as Dippy. And if you visited London as a kid, you would have seen Dippy in the entrance hall of the museum. So the brief was for a new life-size bronze dinosaur based on Dippy to be exhibited outside permanently with minimal visible structure. It was to be life-size, 25 metres long, and made up of the 292 individual bones. It's the length of 3 London buses, and the tail alone is 15 metres. That's a cantilever. Somewhat rashly, we said we could do it with no props at all. We entered the competition and we won. When we talk about the relationship between design and making, then nature is the great designer. And this is illustrated by taking a closer look at one of the vertebrae. On the left is a 3D printed structural node by Arup, which has been optimized by computer program to minimize its weight whilst maintaining its strength. On the right is one of the cervical vertebrae, the Diplodocus, which has also been optimized, but by the power of millions of years of natural selection. Over the course of the project, our Diplodocus revealed more sublime solutions that in turn helped us to find ours. This is the final design. Everything in grey is the natural biology, and everything in colour is additional structure. It's a 6-ton skeleton, the world's first post-tension bronze dinosaur, and it has no props. Essentially, it works like this. A cut through the centre of the dinosaur reveals the engineering more clearly. We explored as many alternative structures as we could think of, including an internal beam solution, a fully welded solution, a cradle solution. But we'd rejected these and returned to the original competition proposal, which was to post-tension the spine. The bones themselves form the main structural components, each vertebra being a separate hollow casting. The spinal cord is post-tensioned with stainless steel tendons, inducing a large compressive force in the vertebrae, allowing it to cantilever out from the centre of gravity, which is magically located in the ilium, the giant hip bone, the natural predetermined point of balance. But how do you take a biological form and apply some engineering? Here I need to pause to credit Structure Workshop engineer Max Clayton. Max and I have worked together for over 10 years, and we worked closely throughout this project, but it was Max who mastered the virtual tools required to manipulate the geometry and to interrogate the structure. And it was these tools which ultimately allowed us to ratify the design. We started from a scan of each bone and applied engineering features, flattening the joints to create perfectly elliptical bearing faces which matched the adjacent vertebrae. We then modelled a void inside and subtracted that from the solid to create a hollow form that would become the cast. This was then meshed, enabling it to be virtually loaded and analysed. That's just one bone, and we did this for the whole dinosaur. Ending with a full FE model that we could manipulate and use to predict behaviour. This model takes 2 days to run on our computers. We probably should have got a better computer, actually. And for a while, we weren't even sure we could get it to converge and provide sensible results. More than any other project I've worked on, the intuitive approach, the discussion, the modelling and the interpretation continued throughout the design process. Simple physical models were used alongside sophisticated analysis to help with interrogation and to help with debate. Making being used to inform the design, here exploring how progressive tensioning of the upper tendon induces upward curvature. And when our early analysis predicted that vertebrae would collapse under the compressive load, our modified design was proven by a full-scale compression test in Madrid. Again, nature had provided the answer, internal diaphragms in the bones to resist buckling and develop additional strength. Those tendons terminate inside the ilium, allowing the forces fore and aft to balance. It's a naturally located stressing chamber, providing access to apply the tension via hydraulic jacks and a space for the permanent bridge and locking nuts. Our design and specification were ambitious and highly demanding. And Adam was keen to remind us that the physical world is far messier than the virtual world. Whilst he reminded us of that, the approach to fabrication was in fact exacting, combining advanced form of digital mediation with ancient artisanal processes, executed by a team of highly skilled craftspeople and technicians. Starting with the high-resolution scan data, we pass from the virtual world to the physical, 3D printing each bone. These are moulded in silicon, using plaster jackets forming an accurate negative of the bone. The mould is then used to create a positive in wax, which gives the process its name, lost wax casting. The lost wax method is truly ancient, and the oldest known examples of this technique are over 6,000 years old, not far from the age of the Fenland black oak table. The wax is invested or entombed in ceramic and protected and supported by plaster, grog and scrim. The investments are then fired in a kiln or a muffler to remove the wax, leaving a perfect negative for the molten bronze to be poured into. The principle is simple, but the process takes a huge amount of skill to preserve the detail, to design the runners and airs which allow the bronze in and the air out, and to handle the large delicate moulds, and to pour in bronze at 1,000 degrees centigrade at just the right speed. Wax distorts and castings shrink, and if the bronze is too hot, the tin burns off, and impurities in the mould can affect the alloy and the quality of the casting. All of these factors and more must be allowed for and mitigated. This process of transformation is the story of design and making. First, a living dinosaur, Death and collapse, bones buried in the silt, a negative impression in the sediment, slowly displaced by minerals to form the fossil, dug up millions of years later, to be moulded in the negative to form the plaster positive that became dippy. Then positive scanning, negative moulding, positive wax, negative investment, before finally becoming a positive bronze casting again. Inevitably, the process produced distortions that did not meet the requirements of the design, and a little like an engine block, each cast vertebrae was rescanned and milled to achieve those perfectly accurate bearing faces. Once cast, the bones could be trial assembled. Before beginning a carefully determined sequence of threading bones onto tendons like beads on a string, and locking in the tension as the form developed. You can see here where the tendon runs along the top of the vertebrae. It was an incredible experience to witness the skeleton slowly come together. There was a huge beast lurking in the workshop, and unsuspecting visitors would be stunned into silence as they came round the corner. In a final act of confidence collecting, the long cantilevers were load tested by hanging what we called the stag do load from both head and tail. 260 kilograms on each, giving me and Adam a heart-stopping afternoon, but the final confirmation that we had designed something remarkable and that Factum had managed to make it. It was delivered in 4 parts by road, requiring a subtle amputation to get under the bridges, and then installed over 2 nights. In the end, it was due to the combined effort of a host of talented and dedicated people working together, designers and makers who realised the significance of the project and the opportunity that it represented. Without props, the true elegance of this mighty animal is for the first time expressed, demonstrating its beautiful detail and balance, the clarity of nature. Last year, the Natural History Museum welcomed 5 million visitors, which gives you an idea of the potential that Fern and its counterintuitive design has to inspire future generations. Certainly, we need their creativity and their wonder to solve the existential problems that face us over the next 120 years and beyond. I've shown you a series of projects where I think craft and material exploration have informed the process, but are there any lessons we can take forward, and are these ideas scalable? Perhaps 3. Firstly, to value what we have, our existing buildings. To resist demolition and allow buildings to learn and adapt, and by willing to invest in their past, their present and their future. This is the Fashion Museum Bath with 6A architects. It's a project to turn a disparate group of existing buildings into a new cultural centre for the city, reusing the buildings that we can and reusing the foundations and materials where we can't. Secondly, when we do build, it should be for future generations, not just our own. Simple, understandable buildings of high quality. Buildings that will engender affection, retention and future adaptation. This is the design for a new block of student accommodation for Mansfield College in Oxford, again with Field and Fowles architects. It takes forward the lessons of those Victorian warehouses, simple, legible, delaminated design, and a low-carbon engineered timber frame with a load-bearing stone facade that can be stripped back, maintained, and readily adapted in the future. And finally, that making things together with our hands, whether that is gardening, knitting, baking, or building, is deeply human. It connects mind and body and encourages us better to understand and value the world around us. Thank you for listening.